Welcome back to The Explainer. Today, we're diving into something I like to call the Great Wiring Mystery: series versus parallel circuits. Over the next few minutes, we're going to demystify those invisible electrical forces that literally power everything in our daily lives, from the lights right above your head to the device you're holding in your hand. We'll explore how they work, why they sometimes fail, and the hidden engineering that keeps our modern world shining bright. Let's get into it. To kick things off, let's ask a question I know you've probably muttered under your breath before. Why does one bad bulb ruin a whole string of fairy lights? I mean, we've all been there, right? You get to experience that visceral frustration of untangling a massive string of holiday lights. You finally plug them into the wall, and you get absolutely nothing. And it's all because of one single tiny burnt-out bulb. It is incredibly maddening, but it's actually a perfect real-world example of foundational physics at work, specifically how electricity absolutely demands a complete journey to do its job. Well, the culprit behind all your holiday light frustration is what we call a series circuit. So what is that? It's basically a setup where electricity travels through components one after another, moving along a single continuous pathway. Think of it like a one-way street with absolutely no detours or side roads. Every single component, every little bulb is connected in one continuous loop, which means there is exactly one route for the electricity to take, from the power source through the lights and back again. And that brings us to the fatal flaw of this design. Break the path, break the power. Because there is literally only one route for the current to follow, if any single component fails, the entire circuit just ceases to work. All the other bulbs in the chain, they turn off immediately, regardless of whether they are perfectly fine themselves. When that one fairy light burns out, its tiny internal filament snaps, and it physically breaks that single path. That one microscopic gap prevents the flow of electricity to any of the other components down the line. Okay, so how do we fix this? That leads us nicely into our next concept, the parallel circuit. Let's compare the pathways of electricity between the two. As we just discussed, the series circuit uses a single continuous loop, but a parallel circuit, it uses multiple paths or branches. It brilliantly solves that single pathway problem by offering the electricity more than one way to flow. If one road is blocked, the current simply takes another route, bypassing the obstacle entirely. This difference is huge when we look at component failure. In a series circuit, everything stops entirely. If just one component fails, boom, lights out. But in a parallel circuit, since there are multiple branches, if one component fails, the others in different branches can actually continue to operate. Their individual paths back to the power source remain perfectly intact, entirely unaffected by the broken branch right next to them. Section 1. Parallel circuits, powering your home. These parallel circuits dictate the very construction of the buildings we live in. I mean, why do homes use parallel circuits in their electrical wiring instead of series circuits? Our source material points to two primary reasons: independent operation and voltage distribution. The engineers designing our homes really needed a foolproof way to handle component failures safely, and to ensure that power is distributed effectively across every single room without any drops in performance. To really grasp the immense value of that first point, independent operation, just imagine this scenario for a second. Imagine if a dead kitchen bulb blacked out your entire house. No way, right? If homes used series circuits, that single burnt-out bulb over your stove would literally cause your whole house to lose power, because that single electrical pathway would be completely severed. It would be pure chaos trying to find the one broken device every time the lights went out. So thank goodness for parallel wiring. With independent operation, one broken appliance or switched-off light doesn't ruin the whole network. The electricity just keeps flowing smoothly through the other branches to keep your fridge running and your TV on. Moving on to Section 2, the brightness battle, sharing the push. Now, I want you to consider this question. What actually happens to the brightness of the bulbs when we add more bulbs to a series circuit? Think about it. If we take that single continuous loop we talked about earlier, and we just keep adding more and more lights to it, what physically happens to the intensity of the light they emit? Do they stay exactly the same, or does something fundamental change in the circuit? Let's walk through the logical sequence here. Step 1, electricity travels a single path. Step 2, because it's a single path, the total voltage from the power source is shared among all the bulbs in the chain. It's kind of like pouring a single pitcher of water into multiple glasses. You know, the more glasses you have to fill, the less water each individual glass is going to get. And finally, step 3, because they are sharing that total variable voltage, each individual bulb gets a smaller share. Each bulb gets less push from the power source, and as a direct result, its intensity decreases and it perceptibly dims. This crucial point is captured perfectly in this quote from our source material. Quote, "Because each bulb is getting less push from the electricity, it cannot shine as brightly as it would if there were fewer bulbs in the circuit." I absolutely love that phrasing. Thinking of voltage as a physical push makes this completely invisible concept so intuitive. When you have to spread that single push across more and more components on a single path, the driving power behind each one naturally goes down, leaving you with a very dim string of lights. So as we wrap up this explainer, I want you to literally look around the room you're sitting in right now. Are the devices around you relying on a single shared path or independent branches? Think about your lamp, your computer charger, your television. How are they wired together right there behind the drywall? Once you really understand the mechanics of series versus parallel circuits, you start to see the absolute genius of modern engineering everywhere. The invisible wiring all around you isn't magic. It's a carefully designed system of pathways that keeps our world shining bright. So what else is hidden right behind your walls?